again, so we got the two z-scores. I just didn't finish this out. But you look up the area here, and you look up the area here, and you subtract. You get the area in between. It's just like any old normal z-score problem now. So I started with this problem, but I made it into this problem. And now I'm like back in section 6.3, where I just make it an area for that, an area for that, and subtract it for the area between. Right? Cool. So that's what I meant by one tweak, and it's the same as always. The one tweak here is up or down by 0.5. Right? Okay. I'm rushing a little bit because I actually... oh, that's so nice of you. I do want to let us out early because I have a plane to catch. I got a conference. Everybody thinks I'm starting spring break early, but I got a conference that runs till Sunday. So I'm like...
Vegas, right?
San Francisco, actually. So, not really sure what's going to happen.
30 to 40% chance of rain. Right?
Oh, Brian. You're like Debbie Downer.
It takes a while. It takes a while.
All right. So here we go. I love you guys. You're all so concerned that I make my plane. So selfless. So I already did a little bit of lecture in 7.3. What I'm going to try to do is I want to get to a point where I can give you this little worksheet and have you work today in groups on just like 3 quick little problems. I think what we did last time, remind me if I'm correct, we had this formula here.
Yes.
Okay, good. That's a better answer. And we said that if I didn't have that, I could use this. I have to use that, right? That's my best estimate. If I got this, that means I took a sample, therefore this must change. And then I want to go up and down this much because I want to say, I think it's what I saw. I think it's the average I got, give or take so much. And what tells me how far to go out is how confident I want to be. So let me ask you this real quick, a little side note. Can somebody tell me how much data is in between negative 1.8 and 1.8? If you could look at that and tell me, that's above and beyond. But let's maybe take a second and actually calculate it, right? Negative 1.80, can somebody look that up for me? It might be true, I don't know. Did I already give you a problem like this?
0.0359.
0.0359 for negative 1.8? Now what about positive 1.8? Who's got that?
0.91641.
And then how to get the area in between? Right? Bless you. 70.9282. So if I wanted to be almost 93% confident, so that's what somebody else said earlier, but almost 93% confident, how far out would I have to go? How many steps would I have to go out from the middle?
2.
Is that 2 steps? Are you sure? How many steps would I have to go out to be this sure? 1.8 steps out, right? Why? Because how much do I catch when I go 1.8 steps out? I catch almost 93%. Right? So the way we normally get it is somebody gives me how confident they want me to be, and then I've got to find these. Let me point something out on the chart real quick. We've already done this a couple times. Like if I want to be 95% confident, does somebody know that z-score? 95% in here. From here goes 2, but we actually know now, if you look at 0.025, 1.96. That'll be for 90%, will be 1.645. Right? Look here real quick. There's a little tiny baby chart on the bottom of the positive z-scores. Right? Little baby chart here says confidence level. So if you want to be 95% confident, it tells you the critical value, that's just the z-score, is 1.96. That's kind of cool. Right? It only has 3 values though. So in general, how do you find it? If I ask you to be so much confident, you cut how much is outside in half, look it up to get the z-score. Then that's what you throw into the formula. I've got to go up and down that many steps. Okay, cool. So that's pretty straightforward. I'll have an example problem here in a minute. A question to ask, well, let's see, what order do I want to do this? Let's do it that way. Getting a little conversations with myself. For an NPQ problem. For an NPQ problem. The mean would be NP, right? And then, so I'm trying to go along with this formula here. Just kind of get a feel for what its confidence interval formula would look like. So plus or minus z. What's the standard deviation of a NPQ problem? Cool, right? Now, here's the thing. If I do n times p, I get this. And again, what's that symbol there represent? Mean of a population. If I actually have a sample that I'm working with, if I get a percentage from a sample, I can't use that. Just like if I get a mean from a sample, don't have to use this symbol, of course. I can't use that symbol. So if I get a percentage from a sample, I can't use this symbol. This P is a percentage from a population. We haven't made that distinction yet because we haven't had to. It's always been from a population. If I want to use something from a sample, here's the funny thing. You put a little hat on the dude, right? P hat. It's not just something you don't want to wear. It's a percentage from a sample. Little P hat dude, right? Go with me here. So it's sort of like if it's wearing some kind of clothing, a bar on its head, a hat on its head, it's coming from a sample. That might be one way to remember this, I don't know. So really this formula then, sort of the same way we took this formula for population information, we kind of made it into for samples information, right? We can take this formula and instead of a P then, I'm going to have a P hat. Now the problem here is this truly a percentage confidence interval? Am I going to get a percentage, give or take a percent? This n times p is not a percentage, is it? It's a number of things. If I had 5,000 people, 11% of people are left-handed, 11% of 5,000 is the number of people left-handed. It's not a percentage. So don't I have to kind of divide by n? Don't I want to get the n out of the way? So just like here, I've got a sample mean, give or take some amount. I want to get a formula that's got a sample percentage, give or take some amount. I want the same kind of thing. And that's the thing you always see on the news. You always see how many people want to vote for proposition whatever, 44%. How many people want to vote for against it? 42%. At the bottom of the screen you see plus or minus 4 percentage points or something, right? You always see that. If you haven't seen it, look for it. It's everywhere they do that kind of thing. And this is exactly where it's going to come from, the give or take some percentage. Right now this is not a percentage, it's times an n. It's not a percentage. I want to divide the n out of there. And yes, right now this is Jeff putting you through the sausage making of where the hell a formula comes from. We're going to use what we get at the end. You never have to do what I'm doing right now again. I just want to show you where it comes from. What can I do with this? Can I cancel the n out? Do they both have the same root? I can't do that unless they have the same root. You guys remember that? It's a little bit of algebra. I know there's not much algebra in stats, but there it is. That's the algebra in stats right there. How do I make it have the same root? Isn't the square root of n squared equal to n? Think about it. What's the square root of n squared? N. So isn't this the same thing? Now I could cancel an n out, right? Okay. So if I cancel an n out, don't worry, I'll put this up here. So here's the official formula for a confidence interval for a percentage. So I've got this one for a mean, confidence interval for true mean. Here's a confidence interval for a true percentage. Our data, give or take how much I'm off by. This many steps. Okay, so let's do an example problem like this. So all that stuff over there is me trying to show you where this formula comes from. Yeah?
The bottom one that says for true percent?
For true percentage, yeah.
Okay, I can.
So if I have like, if I take a sample of gross monthly, let's do my least favorite thing outside of class, and let's make up some data. Let's say we poll 578 gross month students. Find 100% of them are sleeping, right? And find I don't know what 101 of them smoke. I want to create a 99% confidence interval. For the true percentage of students who smoke. So the funny thing about these confidence intervals, number one, they come from a formula we already know. It's really just this formula in the case that I take a sample to find the mean. It's the same stupid formula. Secondly, they have to give me basically all the information. They have to tell me everything. The only thing I really have to look up is the z-score. Can somebody help me out with the z-score now that I told you about the little baby chart? If you look at the little baby chart there, and then I love it. So it kind of makes sense. 99 to get 99%, you got to go pretty far out to catch that much data. That's the farthest we've gone yet. So the z-score for this is 2.575. N is 578. What's p hat? And that's certainly a phrase you did not think you were going to hear today. What is p hat? Yeah. Careful. P hat is a percentage. 101 out of exactly 578, right?
Why do you have the 99% z-score? How did you get that? Confidence.
That has to be given to me. That has to be either given to me or that must be what I myself want to do, right? So I understand that it's really easy to get this confused with the percentage we're working with. This just tells me how far to go out. This tells me directly what z-score, how far do you want to go out, period. My p hat is the percentage from my sample. How do you get a percentage? Part out of whole, right? You cannot tell me a p hat is bigger than 1. Just like some of you guys that calculated percentage probabilities that were bigger than 1, that's just as bad. I can't have a percentage of something that's bigger than 1. I talked to